Welcome to the another session of the seminar. Yeah. This time we have Frédéric Babonneau. He's a professor at Universidad of Ibáñez. He just started here, and he's going to be talking about the research he's doing on electricity markets and optimization. The talk is called "A Systems Approach for Modeling Supply Chains of Electricity Under Smart and Sustainable Development." Thank you very much.
Thank you for the introduction. So today I will talk about in English. So about long-term energy modeling. Yeah, usually it's I won't focus on a particular research here, but more globally I will give you an overview of my recent research in long-term energy modeling, because I have been part of a team. We have developed a model called ETEM that actually enable to evaluate and assess the long-term evolution of a regional energy system. And recently, I have been working on representing more correctly the electrical and the power part. So the electrical aspect of supply chain, the supply chain of electricity under smart and sustainable development. So it's the focus of this. Yeah, can I use this? Is it working? Yeah. So just a forward to just maybe introduce the problematic and the concept. So here. So we all know that the power system entering a transition as, okay, we'll have an introduction of a renewable in order to satisfy some very stringent emission carbon reduction, but as well we need a power storage, ID-based demand management, and okay, there is the introduction of this new concept of smart city, smart system, and smart technologies. So for decision makers, they are facing many arbitrage, many decisions that are available for them for designing effective and robust energy policies. So that's the concept. So in order to support a rational decision and to see what can be happen in the future, it is necessary to have this holistic view, this systemic view of the energy system in place, and what could be the impact of different carbon emission constraints and under different evolution of the energy markets. So that's the context. So in the future, you can expect new challenges for the supply chain of electricity. First, you will have the integration in the grid of new actors with mainly decentralized production, mainly with solar production, but you may have also combined heat production and so on. In order to face this volatile and variable renewable energy from wind and solar production, you need reserve. Okay, it requires reserve, so you need clean backup and storage and so on. So there is also this challenge to address. You can have also a change in demand patterns with introduction of new demands, such as electric mobility. So it might be a very huge increase in demand, in electricity demand. And okay, in order to face all this challenge, you have either to reinforce the power transmission or distribution grid. But this is not the same if you consider the development of distributed energy resources. You will have to reinforce distribution grid, whether if you consider the investment in large wind farm, you will have to have a precise look on the transmission grid in order to be sure that where you produce electricity, you can inject and satisfy the demand that can be at the other side of the transmission grid. But at the same time, with smart city and smart systems, smart technology, you have new options that are offered to the system. So you have flexible loads, so you can adapt the demand to the production in some sense with demand response mechanisms. So it's a way to reduce demand variability, so to help in the demand supply equilibrium. Also, from the electric mobility, you can have you can optimize the charging of the batteries, for example, and you can also have in the future the integration of vehicle to grid. So implementation of vehicle to grid means that okay, you can store in the battery of vehicles the electricity and inject back on the network when it needed. So it needs very huge investment in infrastructure, but if we consider this vehicle-to-grid system, okay, it might provide some new option to address the demand-supply equilibrium. And the other also interesting thing with PV panel is that they can contribute to reactive power compensation. So this is the part of electric production that, okay, there are two parts in electricity, real power that is consumed by everyone and reactive power. And when you have a high share of reactive power, it reduces the share of real power. So this is something that has to be addressed in some grid power grids. So okay, there is this new option that may actually okay, have to be taken into consideration in the assessment of energy systems. So from the point of view of the electrical supply chain of electricity, there will be very big changes. Yeah. And currently we have very few utilities, but mainly in the future we may have many producers located mainly at distribution level. We have mainly today centralized production, but tomorrow we can have a decentralized production with new form of energy. The production is quite stable today with hydro, with nuclear production, with coal production, diesel production. But tomorrow you can have, you will have intermittent and variable production in order to satisfy renewable objectives. Yeah. We change also the paradigm today. When you just ask for electricity, you need electricity. Yeah, production can adapt to your demand. So, but in the future, demand will adapt to production with the use of demand response and smart appliances and so on. So, some part of electricity demand might be shift or can be moved from 1 hour to another hour in the day in order to actually satisfy the demands equilibrium, demand supply equilibrium. And another interesting thing in the future is that, okay, that have to be considered when you're dealing with long-term evolution of the energy system is that in the future we won't actually operate at the transmission grid, but more at the distribution level, because, okay, you have to actually take into consideration that the way that you have many producers of electricity and you have to coordinate everything at the distribution level. So this is okay. So we need, we have developed a system approach in order to take the different dimension into consideration. So the first one is, okay, when you are dealing on the long term, meaning that you are considering an horizon of 2050, for example, or 2030. Okay, you have first to consider techno-economic aspect for investment in technology in the grid. So what will be the optimal pathway for investment until 2030 and 2050? But for each year until 2030, you have to be sure that, okay, you can deal with operation constraints. So it's dispatch problem. So you have to be sure that at each hour, each year, you can satisfy the demand for different energy services, and in particular for electricity. There is another dimension that have to be to be considered here is the energy market, and in particular the electricity markets. So you can compute in the future, you can consider in the future that depending on your location, you have marginal cost of electricity that will be different, that will differ. Also, another dimension is the physical network flow constraints. So, okay, depending on the constraints on your transmission grid, you might prefer to install wind farm on the north or on the south. So it really depends. So you have to take into consideration the physics of power flows when actually assessing the long-term evolution of the energy system, and also consider the possible competition among the different energy forms in the future, depending on the marginal cost of the marginal cost of the prices of imports and so on. So what we have been working on is this complete framework where, okay, this is a model called ETEM SC for smart city. So this is mainly a long-term capacity expansion model with dispatch constraints and so on. Where you have all the different modules. The first one is the techno-economic model. So the model will actually decide or simulate what will be the energy system until 2050, for example, in terms of investment. So you know what will be the installed capacity for the future, the operation management. So it's mainly the dispatch problem. Energy markets is mainly based on an efficient equilibrium markets based on marginal prices, endogenously computed. Power flow physics means that we'll be able to compute the power flow on the different transmission line at every time of the horizon, and a smart city for all the demand response that I will discuss later. And we also have introduced risk analytics, mainly based on robust optimization, in order to take into consideration the many lot of uncertainties that are inherent to this type of models. So you enter all this module in the ETEM SC model, and the model can simulate the evolution of the long-term regional energy system under different constraints, analyze specifically the impact of supply chain of electricity. So I will show you what we did recently. Also, we have used this to assess the impact of climate change, for example. And finally, it is used to support the design of regional energy policies. So the outline of my presentation will be the following. First, I will give you an overview of the model, then the different contribution at the distribution and transmission level, and standard case study. But the model? So the model actually represents the entire energy system from energy supply and demand sectors. So it represents the extraction, import of different energy sources, how it is converted, production of electricity, heat, and so on, and the different technology demands. So it's mainly driven by the demand of services. So what you enter in the model is the demand for heating, for mobility, for cooking, for industrial needs in terms of energy. So it's quite a complete model. So it represents the depending on the disaggregation level that you may want. You have different energy services, and the model will have to decide what technology to use based on the cost and efficiency criteria, what the technology will be or penetrate the market in the future based on this. So I will go more in detail in the next slides. So I don't understand why I show all my slides, because some are hidden. But so usually it's a long-term horizon that exceeds the residual life of existing installed capacity up to 20 or 100 years, in order to see what the technology that will replace the existing one. You have to provide the model the useful demand, so the demand for services for any sectors, and also the price for energy resources that has to be imported by the region. So you can refer to an International Energy Agency to have an evaluation or simulation of the energy prices. we have to start with a quite precise description of the existing energy system. So to see how the energy system works today, what are the actually the technologies that are used for producing electricity, for satisfying the different demand of services. So demand of services for mobility. Okay, if you consider just mobility, you have a certain distance to satisfy every years, for example, and you have to decide in the future if you will have a gas car or electric vehicles or diesel vehicles or whatever. So it's a model that will decide that according to a portfolio of technology. So usually we have to input in the model a big, very huge database of technology with different inputs, so different parameters. So we know the efficiency, the availability for all days, the date of availability, the life duration, and the different cost of investment, of operation, fixed and variable cost. And the model will optimize the system cost. So taking into consideration investment, maintenance, operation, imports, and so on, in order to satisfy all the demands for all sectors, all service, with some constraints on availability of resources depending on your investment. You also have to provide some reserve, because if you just invest in the model, invest in renewable, you have to be sure that you will be able to satisfy the demands, whatever. Even if you have a big decrease of solar production, for example. So there are some, and also storage facilities. And you obtain, if you consider different sub-region, you can have locational time, locational and time of use marginal cost for energy, for different energies. I will skip this. So I was talking about the database of technologies. This is just a small example, just one example of concentrated solar plants, where you have you have to enter the model, the investment costs, the operation maintenance costs, the lifetime of the technologies, the emission rates, and depending on the potential and the bound of the potential. So for each region or subsystem, you have to define what is the potential of development for these particular technologies. But you have 100 and 100 of technology in the database, and the model will actually choose what the optimal technology or the optimal strategy of development of the energy system. ETEM is an optimization model that actually is pretty mathematically is very simple, because it's a linear capacity expansion and operation model. So it's actually compute what will be the capacity in the future for each technology, and how to use it in order to satisfy at each time step the demand. So it's dependent on operation, capacity, importation, exportation, and so on. But it gives also an equilibrium market representation, as actually the optimization routine optimize or simulate the efficient energy market equilibrium based mainly on dual solution indicate price based arbitrage. So this is quite known in linear programming and in energy. So in summary, what do the model is that the input are the current energy system that have been asked to be represented quite accurately to represent the existing situation. We have to provide also the evolution of useful demands, how the demand for different energy services might evolve in the future. Usually it is based on GDP evolution, population evolution, or the regional level. It might be depending on if you develop an industry district or a commercial district, or depending on what you can expect in the future in your region. You have to provide this, which is really important, this catalog of existing and new technology, and some sustainable goal and environmental goal. So meaning that in 2030, I want to have 100% renewable, and what is the optimal pathway to reach this 100, this Réunion capacity. Yeah.
I got a bit lost because you said that you have to feed your model with the demands.
Yeah, it's
technologies which are
it's useful. Useful demands. So it's the specificity of ETEM is that it does not start with demand of electricity or for energy demand. It is a demand for heating, for example. So for heating will be the number of square meters that you have to heat in the future. And depending on your need in heating, the model would choose between gas heater, electric heater, and so on. And then if you choose electric heater, the model will actually decide how to produce electricity, and or if he has to import gas or whatever. So it's the whole chain of energy. But yeah, what is really driven the model is the demand for services. So even for mobility, we don't enter the energy demand for mobility, but the number of kilometers that has to be done by people, and so in order to just satisfy this demand in mobility, the model will invest or decide investment in electric cars or gasoline cars or whatever.
This is focused on a national system.
Usually on a regional, it might be used for national system, but we use it on regional system mainly. So it was what we did in the last in the last decade. We developed this model, and recently we have been working. We have been focusing our research on the power grid. How to represent, because here we have been. I'm working currently for a French Ministry of Energy and the French Agency of Energy, which is called ADEM. And this is the map of La Réunion. This is the French island, and their objective is to reach 100% renewable in 2030. So they want to have an idea on how they can reach this very strong objective and what would be the optimal pathway according to different scenario of price or different scenario of technologies and so on. But depending, and we focus precisely here on the electrical sector. But of course, the way you invest will have an impact on your grid. Because power that is flowing on the grid depends on physical laws, so you have to present correctly physical laws, and there are also some capacity. So if you decide to invest in a big power plant here to satisfy the demand here, you might have a problem. You will have to envision very big and expensive investment in the transmission grid. So what is important is to represent correctly this power flow, this transmission grid, in order to be able to make a trade-off between locational investment in terms of production and transmission line reinforcement. Okay, so yeah, it's what I mentioned here. The question: what are the impact of the power transmission constraints on the energy transition? Do I have to actually consider reinforcement decision? That will be very much expensive, very much expensive. So what I did here is to integrate in ETEM a transmission grid representation, and considering the physical law that determine the way to compute power flow, and then the model will make a trade-off between grid expansion and locational of distributed generation. That's the point. Yeah.
Do you take into account the energy losses?
The energy losses, yeah. Here there are for the transmission grid, we have an estimation of the losses, so we take into account, but it's really no, it's not quadratic. But at the distribution level, we consider it. So we consider an AC representation, which is non-linear and convex, but through linearization and iterative process, we are actually able. But I will discuss this point in the next section. But here for the transmission grid, we do not consider this AC formulation because it was even not very interesting. Usually, it's when you consider long-term evolution of transmission grid, it's enough to consider a DC formulation, and you just have it assumes that you have no resistance. And what we have to provide to the model is the capacity of the transmission line and the substance, because if you have no resistance, you have only a reactance, and so we refer so we have integrated in the model this representation, so this linear DC formulation of the transmission grid, and actually, if you have different nodes, it will compute the powers that flow in each line that satisfy actually also the capacity, physical capacity of the line. And the model actually compute nodal marginal pricing, taking into account these different physical constraints, and one can also reinforce the transmission line in order to satisfy, to make this trade-off between the different possibility of I would say of investment. And here, just to show you what we obtained, the first result that we obtained for this French island, La Réunion. So in terms of installed capacity, so it's really aggregated at the island scale, but we have very detailed, I'll show you in the next slide, but very detailed results at each node, each hours of the day, at each day of the year, each year of the whole horizon until 2030. But what we obtain usually, it's if you want to obtain in 2030 here, you have a big increase of solar production, but as well in wind production, and also biomass, and also some, it's not very easy to see here, but we have an increase in hydro production as well, and geothermal production, which is green part here. But in terms of mix, you see that you have a decrease in diesel electricity production, coal, which disappear in 2030, and this is replaced by only renewable production. And for this scenario, we have the evolution of the electric marginal prices that are given by the model, which correspond to this line. So we have a quite significant increase in electricity, but it's a long-term electricity marginal price. And in 2030, we can have this kind of mix. And here I just show you what is a power flow for the first semester, but for each hour of the year in 2030, we can see how demand is satisfied according to different energy production. But it's very aggregated, for example, because for example in biomass you consider I don't remember, but 5 or 7 different technology of producing electricity from biomass. Hydro we have from dams, from irrigation, from whatever. We have plenty of technology here in order to satisfy the future demand. And this is not for nodal production. This is for a given node of the distribution level. We see for a typical day, for 4 typical day, what are the profile of production. Clearly, it is a wind solar production with production in the day. So and we also compute for each time step the flows that the powers that flow in each transmission line in order to be sure that demand is satisfied and we respect all the physical constraints of the transmission grid. And the model actually computes 2 reinforcement investment for 2 transmission lines that correspond to abundance, which is this one and this one. So this is very detailed. So it's what we are. I'm currently working on from. Yeah.
That's with real power data, load data from the place, right?
It's real. This is. These are power flow that are computed by ETEM, by the model, and the load are actually input in the model, are the input of the model. So we know the demand, the load here at each node in 2030 at each hour, and we have to satisfy this. So this was at the transmission level. Now from the distribution level, so from to take into consideration smart technology, smart city concept. Okay, here the objective was to model distribution option and constraints. So so the idea and the objective here was to model more accurately distributed energy systems. So at the demand side, we have to take into account the possibility to move your demand from one area to another, so which is done by demand response mechanism. Also the possibility to optimize EV charging. So we know that, okay, if in 2030 you have an operator that decide to change your charging pattern because there are some requirements from needs from a systemic point of view, might be possible. Also from the production side, we have to represent correctly the distribution energy, solar, V2G, okay, the possibility that, okay, the battery of vehicles can be used as a reserve or as a provider of electricity. So you can, as I told you, you can store at some time, okay, you charge the battery and you use this battery as a storage capacity. So when you need more electricity on the network, you can use this, a part of this electricity. So the objective is to address, is to assess the role of these distributed systems, how they can help in the demand-supply equilibrium, provide secondary reserve requirements, so in order to stabilize the system, and also compensate for reactive powers. So our assumption here, okay, it was not possible to represent a very detailed distribution grid in a very big model like ETEM. So we actually represent each distribution feeder by one node. So it's really aggregated. From at each node, we have an estimation of resistance and reactance of the whole transmission distribution grid. At each distribution feeder, we have flexible demand, conventional demand. We might have also demand for EV charging and so on. We can also have distributed energy production from solar panels and so on. And all distribution feeders are connected to transmission line, but we don't represent transmission grid, but we don't represent transmission grid. So we have centralized production that actually can contribute to satisfy the local distributed demand, and at the distribution level, you also have distributed production and demands. Yeah, and what has been done is first to model demand response and V2G, vehicle to grids. So demand response, what has been included in the model is mainly for heating and cooling demand. So instead of satisfying directly let's say a demand for heating, we introduce in the model some dynamical equation on the evolution of temperature, inside temperature. So the model, okay, has a comfort zone. So we know that for each building, you want the temperature to be between 18 and 21. And the model can actually, okay, have to satisfy this the demand for to be into the comfort zone, but can actually, according to the need of the system, reduce your temperature, increase and optimize what the optimize the energy consumption for heating according to this comfort zone. So it gives some freedom to the model to actually I would say to actually adapt to production variability. We have the same idea for vehicle to grid, meaning that for people we have constraints in terms of charging. So we have I would say range of charging, constraints on charging, and the model can actually use electricity into from the battery for satisfy other demands according to these charging constraints. So usually in the evening, where people use their car, you want your battery to be fully charged, so you cannot use the electricity from the battery, or you are less freedom on that part. But there are some dynamics that actually represent these constraints and the charging of the different batteries of electrical vehicles, and the model can actually use this reserve to satisfy other demand and to adapt to the electricity production. And this is a typical example still on French island La Réunion, where you have the original load curve here in black line, and the model here use only the possibility to optimize load with EV charging, so optimize EV charging, and he move some demand from one part to the other part here. So it reduces the peak in the evening here to adapt the production, the supply to the demand. And you see that in midday you have a lot of solar production, and this is stored in the battery and inject back in the network when needed. So there are some smart behavior of the model. The other improvement that have been added in the model is how to model correctly. I would say the reactive power and the losses at the distribution level. So for each distribution feeder, we have to compute what has to be provided by centralized production. So it's just a balance between distributed production and demands. So, and you have for real power and reactive power. And here we consider an AC formulation of power flows. So as you know, this is quadratic. So you have power to the square of real power and reactive power, and when you put it in the model, it's really very difficult and impossible, intractable. So what we did here is that we linearize the equation and we update this linearization iteratively. So we first linearize, we solve ETEM with this linearization, and we change the linearization point, and in practice it converges in 5 to 10 iterations. So it's quite very rapid in terms of iteration, while the model still take a few hours to be solved. So at each iteration we have to solve a model that it's quite time consuming. So here I will just a study that we did for a Swiss context, the Romandie. So actually this Swiss region has 3 distributors. So we represent the 3 distributors and assume that you have smart technologies that penetrate in the system, and actually you will simulate who is providing reserve and reactive power locally at the distribution level, and to see how this reserve and reactive power could move from okay, the current situation is mainly at the centralized level, and it is replaced by a situation in which reactive power and reserve is mainly provided at the distribution level by PVs for reactive power, and here it's and flexible, it's EV, electrical vehicles. And you'll see also for secondary reserve requirements, you see that the transport here is able to provide this reserve by exploiting this facility of adapting, and also with the ETEM. But okay, I don't want to spend more time on that. So finally, what did the model? What does the model is the following. So you still enter the current energy system, but now you have to enter the technical parameter representation of the grids. So either transmission grid or the distribution grid. So now that at the moment, the transmission grid cannot work with together with distribution grid, because one is in DC formulation whereas the other one's in AC, so it's not compatible. So that will be the next step. And now the model actually can compute at the transmission level the reinforcement in terms of transmission line, but as well compute in an approximate way for the transmission grid, in a precise way as a power flows. We have also the losses, which is not mentioned here. Also, you have a distinction between real and reactive power, reserve requirement, and also optimal demand strategy, or demand response strategies. So it's quite complete. Yeah, and what I've been working on recently as well is how to represent and to take into consideration the different sources of uncertainty in the model. So yeah, the model is quite huge. We introduce also this this possibility, and okay, I just want to mention here that we are take into consideration uncertainty in energy prices, technology costs in terms of investment, operation and management. So all this is in the objective function, but as well in the constraint, technology efficiency and availability, useful demands, and we are able to take into consideration all this is uncertainty in the same scenario, in the same simulation. And there are two advantages on using robust optimization here. The first one is, okay, you have a reasonable increase of model dimension in terms of constraints and variables, so the model is still tractable, and we have a possibility to model many uncertainties. Yeah, and the second one is, okay, you have this, it reduces this bang effect that is actually linked to linear programming, and it goes to diversification in technology portfolio in investment and in the mix. And it's quite interesting because, okay, usually you have for each scenario of uncertainty, you have this scenario analysis. So for a policymaker, you say, okay, this optimal you have an optimal investment strategy if you have this scenario of parameter of uncertainty. But if you consider this other scenario, you have a very different optimal investment strategy. So somehow the decision makers or policymakers are lost between the different possibility optimal strategy in terms of investment. So whereas considering robust optimization, we actually are able to propose an optimal investment strategy that actually is this robust, it remains good, whatever the realization of all uncertainties. So somehow, but okay. And yeah, here you just have a small example. The typical behavior of linear programming, where, okay, depending on the cost and efficiency in the transport sector, here you have the whole sector that actually is penetrated by hybrid vehicle. And in 2050, you have only hybrid vehicle, whereas when considering robust optimization, you have more diversified features. picture. How much time do we have?
10 minutes.
10 minutes, okay. So finally, I will just discuss the case study that we already mentioned with Roberto and Adriana in Qatar. So here, it was actually a study, so a research project to analyze what could be the impact of smart energy system in the future of the energy system of Qatar, in particular in Doha. And it has been a research project with HEC and a local partner in Qatar. So we had to represent the existing system. So you have to know that Qatar is the energy system of Qatar is based mainly on gas. So all electricity is produced by gas, and they are extracting also gas for exportation. But we do not consider this part of the industrial activity. So the first step is to represent correctly the existing system, energy system. So we have represented the electricity supply, the private transport, and somehow the gas industrial sector, water desalination, which is very energy intensive user. And also residential, and okay, we have to get all this data from different sources. Yeah, I won't go very much in detail, but okay, we have to get all information regarding gas, LNG, and oil sector, power, water desalination, and we were able to represent the existing sector and to retrieve actually the CO2 emission in 2012. According to different sectors. So the second part, so you have to provide a model with demand of services, useful demands, so that are based mainly on GDP evolution, population evolution. So you have, for example, the demand for cooling, for captive electricity, for you have different. Also the demand for water. And the demand for private sector in thousands of kilometers. And okay, we have considered different scenario here of evolution of the energy system of Qatar that we compare to the business as usual. Okay, I don't want to discuss every scenario here, but just to show you what kind of analysis and results that we got from this. Okay, what is really important here, I want to highlight here, is the smart city scenario. We actually use a model to assess what could be the impact of developing and implementing new smart district in Doha, because they're actually building a new smart district that is called Lusai. And what if we reproduce this smart district development for 30% of new districts? So we consider that 30% of new districts will be smart, meaning that, okay, they will build upon this paradigm of smart integrated transport. So we have public shared transport, which is more efficient, and also smart district cooling, which is also more efficient in terms of energy consumption. And we assume that at least 30% of new districts in Qatar will have this trend. And what I wanted to just go to the final. Okay, so we evaluate and assess the evolution of the energy Qatar system on 2050 based on the smart city paradigm. So, and we compare two situations. One where you do not consider the smart districts implementation, and the other when you consider the smart district implementation. But when you consider this smart district, you have to consider the cost of implementing and building this smart district. That we didn't have this information of the overcost of smart district. So what we did is, instead of integrating, so we just do not consider this cost, this additional cost of smart district, but we see what could be the avoided cost of the saving costs in terms of saving energy by using this smart concept. And the difference was about 10 billion avoided costs on the whole horizon if you consider smart district instead of not considering smart district, traditional development. And okay, how to interpret this $10 billion? It's that okay, if the additional cost or the extra cost of building a new smart district is higher than 10 billion, okay, maybe it doesn't make sense to go in that direction. If you estimate that the extra cost of this smart district is lower than 10 billion, okay, it might be a good decision. Yeah, in conclusion, yeah, I will just go to my final slide. So now we started working with SNIL and Tito on a new project, and I hope I will succeed in my Fondecyt submission because it's related to this, but we already started working on that. And here the objective is to explore advanced operation research technique. Operation research technique. Would like to experiment the possibility to include in the model distributionally robust optimization and also stochastic programming in a smart way. Also to link with actually this smart technology, I would like to consider social acceptability of acceptance of smart technologies in order to have an idea of what could be the probability of penetration for these technologies and introduce this in the model. I'm currently working with a colleague from Switzerland to complement this analysis, macroeconomic analysis in terms of employment and so on. And okay, with SNIL, we'll start a case study on Chile and more precisely on Santiago, maybe, okay, depending on the available data and so on. So yeah, and there are various papers that can be consulted that are either yet published or submitted. But, yeah.